All right, this video is about functions, function notation. We're going to cover composites and inverses as well. So let's see what it's all about. Okay, first of all, let's have a think about this equation here, y equals x squared plus 3x. This is something that's quite familiar, I think. It's we could draw a graph of this, obviously, put y on the vertical axis and just plot it out. So that's okay. We could write it like this: y of x, y brackets x, and this just kind of signifies really that the y, or the thing that we use to calculate y, is made up of x's essentially. So that would be sort of normal kind of notation. Then if we want to evaluate for a specific value of x, say in this case 2, then we just substitute 2 in for every occurrence of x. That gives us 2 squared plus 3 times 2, evaluates to 10. So that's fine. So this is kind of useful notation, isn't it? So we've evaluated y when x equals 2. So we use that quite frequently. Now, what would we mean by this, y of 2x? Well, we just follow the same plan basically, and what we do is for every occurrence of x in our function here, this is the function on the right hand side, we would substitute 2x. So in this case we get 2x all squared plus 3 times 2x, which comes to 4x squared plus 6x, should we simplify it. Now, 2x itself, of course, is a function. We could call that z of x equals 2x, z equals 2x. In which case we could write this. Okay, so this left-hand side here, we recognize this as a composite function. Okay, so that's really what we are talking about. Okay, so let's just move on and let's just have a think about this. So the important thing, I think, is that we don't have to use y and z. They're just letters at the end of the day. And usually when we're covering this topic, we tend to use not y and z, but f and g. The ones, the letters that appear most frequently. So let's just have a look at an example of where we're forming the composite. Say we've got a function g of x, which is 3x plus 1, and f of x, which is 2x plus 5. Okay, so that means if we put a value, let's say x at this stage, into this function, we get something out that we can call g of x. Then we put that number into this function here and evaluate that. And what we get out is this f of g of x. So we're applying f to the outcome of the g function. Here, if we were to evaluate f of g of 2, and incidentally, it's more normal to miss out these parentheses here and just write it like this. Okay, sometimes we put a little small circle in between the f and the g. It's just a different notation. But here we got f g of 2 equals 24. Now, incidentally, if we did it the other way around, we formed a g of f of x, then what we do is we put our value of x into f function. What we get, we call f of x. We put that therefore into the g function, and what we're getting is g of f of x. So as we move to the left, basically, or outer, then those are the sort of later stages of the compounding of functions. So here g of f of 2 is equal to 36. So a different answer, and in general, f of g and g of f are not going to be the same thing. Okay, just a little note here that I've marked down is that we're talking mostly about the composites of two functions. But in actual fact, there's no reason why we can't. So, string another one in there as well, and do a composite of a composite, and so on, ad infinitum if you wish. But most of the examples that we're going to be looking at, both at GCSE and at A level, will just really be two functions. Okay, so I suppose we need to ask the question: why do we need to do this? If you know that a function is x squared plus 3x, then why do we need to call it f of x? Well, the point is that there are a lot of rules and formulas in maths that actually are to do with functions, whatever the function is, in terms of the way that some of our helpful rules and equations apply to functions. So perhaps we can sort of think of the idea that in your early years maths, that it's all about numbers, isn't it? We deal with numbers, and then as we sort of advance, then we're interested in unknowns and variables, and we have lots of rules that apply to how we deal with with unknowns, how we solve equations, for instance, things like that. And then as we go more advanced, we're actually interested in how we handle functions and the relationship between two or more functions. And so to be able to have a language that we can use for that is actually quite useful and important. Just as a simple example, we've got the inverse function, the idea of the inverse function, such that if a function takes some value of x, just like in our number diagram, and we convert it into a value of f, or f of x, and then we've got another function g which takes that resultant value and converts it back to something which turns out to be the original value. When we kind of reverse the process, haven't we? Then those two processes would be those two functions would be inverses of each other. So the first one was f, then the second one we would describe as f inverses. So this is the notation we use, f minus 1, a little bit confusing because we're kind of used to thinking of something to the power of minus 1 as being, well, it's a reciprocal, isn't it? But in actual fact, a reciprocal is a multiplicative inverse. So it's sort of the same thing. So here's an important rule for starters. The composite of the inverse of f and f of x equals x. So there's a good rule, fairly straightforward one. Let's just have a look at this example here. So if we've got function 2x plus 5, and we put our x into that, we get f of x out, and then if we then take the inverse. Now this is the inverse function. I'll come back to this, why it's this in a moment. Then we'll put our f of x into that, and we get x out. So just to look at that, if x equals 2, got 2 going in there, we're going to get 9 out at this stage. Then we put 9 into this, 9 minus 5 over 2 is going to be 2. So we've applied our function and then our inverse function, and we get back to where we started. So what we're doing here, well, if this is the inverse, we apply this, and we're actually putting this into every occurrence of x in the original function f. Well, we've only got one, haven't we? That's here. So what we're forming is 2 into x minus 5 over 2 plus 5. Well, we can just work that through, and actually we can see, if we simplify this expression, we can see that actually is actually equal to x. So in some situations we can find the inverse by reversing the things that we do, and doing them in the reverse order. So here we're multiplying by 2 and adding 5. So here what we're doing is we're subtracting 5 and dividing by 2. So for simple functions, linear functions, we can do that. If the functions are a little bit more complicated, then we have to change the subject of the equation, which you will have done under a separate topic, hopefully. If not, there's an example a bit further down which will illustrate this. Now, you may or may not have done some calculus. If you have, then here is a useful rule that the derivative of product, I've gone back to using y and z here, the product of two functions, y and z, is equal to the derivative of y. That's what this y prime is a sort of abbreviation for. Y prime times the function z plus y times the derivative of z. Okay, so there is quite a good rule as to how we form the derivative of the product of two functions, regardless of what those functions actually are. In some situations, we might have to constrain the domain of the function. So we just sort of say, well, this applies for x between 3 and 8 or something like that. But within those constraints, then this is a really important and useful rule. Okay, so that is what we do. Yeah, we're kind of not applying functions, I guess, too much GCSE level. But what we need to be able to do at GCSE is be able to manipulate them, derive composites and inverses, and work with them. Okay. So just another thing that we might say, just to perhaps help visualize this, is that if we look at functions and their inverses, then we represent them graphically, they do actually represent a reflection in the line y equals x. Kind of quite useful, and gives a good sort of visualization of what's going on. Why is that? Well, in some sense, we are just reversing the axes, and of course, if we're finding an inverse and we're doing that by changing the subject of the equation, then you can perhaps see how that is the case. So if we look at our previous example, so we've drawn this red line is function 2x plus 5, and the blue is its inverse. I mean, say neither of these is actually the inverse. They're inverses of each other. So if, for instance, we put the value 2 into 2x plus 5, we get 10 out, which is going up and along. And then if we put 10 into x minus 5 over 2, along, we get 2 out. And then this is true for other things. Here's the red one is y equals x squared. And the blue one is the square root of x. I think we can probably see that now those are inverses of each other, and we can see they actually are reflections of each other in y equals x, which is the green line. Yeah, sort of going on to things that apply more specifically to A level. If we've got this red line, which is function e to the power of x, then its inverse is the natural log of x. Okay, so if you're not sort of, if you haven't covered that, then don't worry about that, but that'll come into some worked examples. Okay, so, and mentioned the maths life cycle already. So that's what that is. All right, so look at one or two examples then. All right, f of x is x over x plus 2, g of x equals x squared minus 2, work out f of g of x. Okay, so what we are doing is we're plopping this x squared minus 2 into every occurrence of x in f, and this is what we're going to get that. So that's our x becomes that, this x becomes that, and then if we work that out, and just simplify that, obviously x squared on the denominator, divide through by x squared, and we get 1 minus 2x to the power of minus 2. That's what we've got here through this process. And there we go. We've already expressed it in this form: a plus b x to the power of n, where a is 1, b is minus 2, and n is also minus 2. So that's a fairly straightforward example, and not untypical of the sort of thing that you might get. How about this? Functions f of x and g of x are defined as follows. F of x equals a half into 4x minus 3, and g of x equals this 0.5x plus 0.75. Find f of g of x. Okay, so this is what we want, therefore, is f of g of x, which is this. So if we then apply the f function, what we're going to do is we're going to multiply what's in the brackets by 4, subtract 3, and then take half of the total. And there we go. So that just that's going to give us a half into 2x plus 3 minus 3, which clearly equals x. And then if we do the functions the other way around, yeah, okay, g of half of 4x minus 3, being f of x. And that's going to give us this, work that through, and again, we're going to get x out. So we can see, I think, from this that f and g are therefore inverses of each other. And so what we've worked out for g is actually also the inverse of f we've got there. And the domain and the range, well, the domain is the set of values that we can put in to this function, and the range is a set of values that actually come out. So just as we, with these two functions, put all of the real numbers, then we can do the same thing with this. You've got to watch out for situations where, for instance, we might be divided by 0, or these are just linear functions. So, you know, our f is just a straight mapping between x and f. For every x we put in, there is only one value of f. Now, that's not always true. You know, if we think about a circle, for instance, you could put one value of x in and get two values of f out of it, in which case we might have to constrain what we're allowed to do in terms of the domain. Okay, so that is a useful example, I think. Now this one is a bit more tricky, actually. Let's have a look. Functions f and g are such that f of x equals x plus 25, g of x equals x squared minus 12x, and h is the composite of f and g. The domain of h is x is less than 6. So let's find the inverse of h. Okay, well, h is f of g of x, so let's just work that out first. F of g of x, so what we're doing is we're taking g of x and putting it into every occurrence of x in f of x, so that's what that does. And quite simply, that comes out to this function here. Right, now we've got to change the subject of the formula if we're going to find the inverse. So that's a process I mentioned a few moments ago. Right, so in order to do that, we need to, not completely obvious this, but we need to complete the square here. So in order to do that, we need to get it into a form that can be completed. So what we've done there, we've added 11 onto each side. I'm just calling h of x h because it just makes it a little bit easier to work with. So therefore, h plus 11 equals x minus 6 squared. And x minus 6 is plus or minus h plus 11. Right, okay, so just moving the 6 over to the other side, we've got x is equal to 6 plus or minus the square root of h plus 11. Now, the thing is, we've got plus or minus here, so we just have to think a little bit about this. Now, the domain, this is an important bit here, the domain of x is going to be the range of the inverse. So it's the set of things that can come out of the inverse function. So if we use the negative of this square root, then that is going to give us a range less than or equal to 6. Yeah, not completely obvious that, is it? But anyway, that's you have to work that through yourself, I think, in slower time if you're not convinced. So therefore, Rx is equal to 6 minus h, square root of h plus 11, and at this point, then we swap the variables around because we always want the functions, whether they be inverses, expressed in terms of x. So we just swap those over, and that's going to give us that the inverse function, therefore, is 6 minus square root of x plus 11. Okay, right, just we can illustrate that graphically. So this red line here is the quadratic that we've got from the composite of f and g. So it's a fairly familiar thing. Here's the line y equals x, and this is the inverse that we have calculated. Now note it's not, this kind of goes round and round. So if we were to actually twist this round, as we've done with the other examples, you'd expect to see a blue line over there. But of course, then we'd have a situation where we've got more than one value of y for a value of x, and that's something that we don't allow ourselves in the thinking about functions and inverse functions. So that bit has basically been chopped off. The top bit would be the plus. Yes, we've taken that out of the situation. So if we just constrain ourselves to x is less than or equal to 6, then where you can sort of see here, can't you? We've got this line here and this line here, and this kind of is y equals x sort of bisects the two, so that the red and blue are reflections of each other in that green line. So yeah, so that's how we do that. Yeah, this is kind of a little bit more complicated. We could see simpler examples of this, where we didn't have to kind of think through this a little bit, which takes a little bit of thinking through. But that's what that is. Okay, and now basically one more example here, I think, and that will do us. So we've got two functions, f and g, domain in the real numbers. Given that f of x plus 3 is this lot, find f of x. Okay, so that's the first thing. Right, okay, so what we've done is we've started off with something, and then we've substituted x plus 3 in for every occurrence of x in that original function. So we want to find that original f of x. So I think the way to do this would be, let's work backwards. So if we subtract a 3 back off, then what we're going to get is this expression here. Well, of course, what we've done here is x plus 3 minus 3, isn't it? That's f of x, and that works out to be x cubed minus 1. I think that's the best way of doing it. I mean, if you're not convinced, you could think of it like this as a sort of alternative solution in this box. Y equals x plus 3, therefore y minus 3 equals x. So what we've got, if we just write this out with y's in instead of x's, we get this. And then we'll just do what I've done really, and subtract 3. We get this, and that gives us f of y equals y cubed minus 1. And therefore, let's do again, it's just letters. We can change the letters. F of x equals x cubed minus 1. So, you know, it might help to look at it like that. If you don't, if you're not clear about that, then, you know, pause the video and just convince yourself. Okay, given that g of f of x equals 3x cubed minus 3, find g of x. Now, it's not necessarily that easy to do that, but in this situation, I think we can see that if we factorize 3 out, we get this expression 3 into x cubed minus 1, and therefore g of x is going to be 3 of x. And I think we can see that if then we take our f, which is x cubed minus 1, and put it into every occurrence of this, we're going to get 3x cubed minus 3, and that will be g of f of x. And f of g of x, well, we're doing the opposite. We've got f and g, so we can just compound them in the way that we have been doing, and we get this expression 27x cubed minus 1, which of course is different to this one. Right, so there's a few examples there. There will be more worked examples on these, both sort of GCSE level and A level. So hopefully you have found that interesting. Thanks for watching this video.